Welcome back to Tech Break by Friday. I am Paraskevi Kivroglou and this is episode 3 of our AI Demystified series. Today we're talking about a powerful term in the AI world, neural networks. Most people listen to the term and wonder what it is. So let's dive into the episode and figure it out. What is a neural network? A neural network is a computational model inspired by the human brain. But let's be crystal clear from the start. It's inspired by biology, it's not a digital copy of it. The difference matters here because one of the biggest misunderstandings is that these systems think like humans do. Picture a network of nodes. We will call them neurons, connected in layers. Each connection has a weight, which means that it gives that specific node a more important or less important meaning. Basically, it means that the information is more or less important based on the weight of the node. When you feed data into the network, it passes through these neurons layer by layer, getting transformed and refined along the way. Without special mathematical functions called activation functions, neural networks would have been limited to simple straight line relationships. For example, saying house prices only go up with size, which, as we know in the real world, that's not actually true. Activation functions are mathematical functions that introduce some sort of complexity and allows networks to learn carved and intricate patterns, like understanding that house prices depend on size, location, neighborhood, quality, and dozens of other factors in complex ways. Think of activation functions as decision makers in each neuron. They ask, is this information important enough to pass along? This simple question, repeated millions of times across the network, enables the system to learn incredibly sophisticated patterns. So, let's explore the anatomy of a neural network. Most neural networks have three types of layers: input layer, where data enters; hidden layers, where processing happens; and output layer, where the result comes out. Think of it like making coffee. The beans, raw data, go in, they're ground and brewed, hidden layers, then you get your espresso output. Each layer refines the input further, extracting more sophisticated features. Early layers might detect basic patterns like edges in images or simple word combinations in text, and deeper layers recognize more complex structures like faces, objects, or nuanced language meaning. So you can see that the size of your network and how many layers it will have depends on the problem that you're trying to solve. So if you're trying to solve a more simple problem, you might need a smaller network. If you try to solve a really big and complex problem, you might require more layers, which mean more complex structures. So, neural networks learn through a process called training. First, they make a guess, say recognizing a cat in an image. If they get it wrong, they use a method called backpropagation to correct themselves. So let's go through this process step by step so you can understand a bit more how this happens. The step one is actually when you have a forward pass. What does this mean? The network makes the predictions, let's say identifying the cat in the image. Step two, error calculation. There is a function that is called loss function, and it basically measures how wrong the prediction was from what we wanted to predict, basically. Think of this as a very precise grading system. It gives you back like some sort of number how wrong you were. Step 3, backpropagation. This is where the magic happens. The network traces back through every connection, like through every node, and asks this question: how much did each connection, basically its information, contributed to this error? It's like some sort of detective investigating which decisions led to this mistake. It's kind of cool if you think about it. So, step 4 is weight adjustment. As we saw before, weights actually measure how important or less important are some informations. So, using algorithms like gradient descent, the network adjusts its millions of connections weights simultaneously. It's like fine-tuning all the components of an orchestra, let's say, where every musicians adjust their performance based on the overall sound. But basically, what this does is that it adjusts all the weights based on this back propagation, because you want to find how less important a decision is in order to come to the true outcome that you want and actually get um, lower error rate from the loss function. So the training is a bit challenging in neural networks because they need massive amounts of data. GPT-4, for instance, was trained on approximately 13 million tokens of text, and if we actually measure it, it's roughly like millions of books. And it's kind of like critical issue if you think about it. If the training data contains human biases about gender, race, culture, the AI learns and can amplify those biases. So this is a consideration that researchers and AI engineers that they are training these neural networks need to always keep in mind, since these biases have ethical consequences. If you really want me to make an episode on that later in the podcast, I would really love to do like a biases and ethics episode. This is really interesting. So there are also common misconceptions on what a neural network actually is. So let's take it myth by myth and debust the whole situation. So neural networks work like human brains. This is myth one. This is not like it's not exactly like this. Like as we said before, neural networks are inspired from the human brain, but in the reality they are mathematical models inspired by brain concepts, but they operate a bit differently. So your brain uses electrical signals, hormones, incredibly complex biological processes that we can barely understand. Like a neural network actually uses mathematical functions and basically compute power, which is, if we actually translate electricity. So myth 2, bigger networks are always better. Reality, as we said before, bigger is not always better. Like larger models can suffer also from overfitting, which is actually I will give an example. Imagine studying by memorizing like every practice test question instead of understanding the underlying principles. So what this does is that you perform only on the practice test questions that you have seen before, but not the new ones because you don't understand the technology, the terminology. So this is exactly what the model does. The model performs perfectly on the training data, but fails on new problems. And balance is the key here. Myth 3 is that AI understands meaning like humans do. So, in reality, neural networks excel in pattern recognition and statistical relationships, but they don't understand it in the way that we humans do. So, when ChatGPT, for example, which is what most people have in mind as AI, discusses emotions, it's processing patterns in text about emotions and it's not able to experience emotions. Um, Myth 4 is that neural networks are infallible. So the reality is that they inherit biases from training data, as we discussed before, and they can make confident sounding but completely wrong predictions. And this is why human oversight really remains crucial, especially in critical applications. So that wraps up today's deeper dive into neural networks on Tech Break by Friday podcast. I hope you know now how to see these systems as not like a mysterious black box, but as a powerful and evolving tool that it can have incredible capabilities and significant limitations along the way. Don't forget to subscribe and share this episode with someone curious about AI revolution happening around us. Until next Friday, keep learning, stay curious, and keep building. Thank you. Have a great week.